Hello everyone, and welcome to part 2 of the exam questions walkthrough on Argand diagrams. If you haven't seen part 1 yet, I would recommend watching that first, as the questions build in difficulty and part 1 does contain some heavyweights. I'd also recommend giving the questions a go yourself first to see how far you can get, and as before, please don't worry if you use a different method to me. Mark schemes always credit multiple methods, and whilst I prefer to think geometrically as possible, of course everybody works differently. And finally, if you find this video helpful, I'd really appreciate it if you could share it with anybody else you know who needs it, so we can reach out to as many people in the further maths community as possible. Without further ado, let's get into the questions. So the first one here, we've got two conditions. Arg z is pi over 3 and arg z minus 4 is pi over 2. And we need to find z in Cartesian form and then modulus argument form. So as always, I'm going to start with a diagram. So for arg z equals pi over 3, we should know by now that that's going to be a half line. In fact, both of these are going to be half lines. So to draw that on, it's going to pass through the origin, that first one, like this. So this is the half line for arg z equals pi over 3. And this angle here is our argument, pi over 3. And for arg of z minus 4 equals pi over 2, we're going to be looking at the point 4, 0. And argument pi over 2, that's just 90 degrees. So we're just looking for a line which goes straight up from that point, like that. And what we're looking for, which this diagram only just shows, is the point of intersection between those two half lines, because that's when the two conditions are going to be satisfied at the same time. So what I'm going to do is work out the Cartesian equations of these two half lines and then solve them simultaneously. So I think the green one's the easier one, because we know that this angle here is a right angle, and therefore the equation of the green line is going to be simply x equals 4. The equation of red line is slightly more complicated, but we went over in the previous video about how if the argument is pi over 3, then the gradient of the half line is tan of pi over 3. So in this case, we can write this as y equals tan pi over 3 x. And tan pi over 3 is root 3. So this is just y equals x root 3. So we're going to solve this one and this one simultaneously in order to get the solution for what it is. So y equals 4 root 3 and x equals 4. And in Cartesian form, that's going to make z 4 plus 4i root 3. And to convert that into modulus argument form, which is quite a standard process by now, the modulus of z is going to be the square root of 4 squared plus 4 root 3 squared, which gives 4 squared plus 4 root 3 squared, 8. And for argument of z is going to be inverse tan of 4 root 3 over 4, which is, I think this appeared in an earlier question on the previous video, pi over 6. So that in mind, we can write z as z equals 8 cos pi over 6 plus I sine pi over 6. And that's said in modulus argument form. So that's the solution to that question. Moving on to the next one. We've been told to find the Cartesian equations of the locus of points representing the modulus of z plus 10 equals the modulus of z minus 6 minus 4 root 2i. So this one, where we have our two moduli and we want to find the locus of points when the two of them are equal. I phrased that really badly, but it's going to be a perpendicular bisector. So for 6AI, it's going to be a perpendicular bisector that we're interested in. And should actually draw an Argand diagram here, just a sketch. So for z plus 10, we're looking at somewhere here, and 6 plus 4I root 2 is going to be somewhere around about there. And we want the perpendicular bisector of those 2 points. So if we join those 2 points up approximately like that, then the perpendicular bisector of them is going to be somewhere around about there, passing through the midpoint. So in order to do that, we need to first find the midpoint between those two. So we want the midpoint of -10, 0 and 6, 4 root 2. So that is going to be, so the midpoint of the x between -10 and 6 is going to be -2, I believe. And then for the y coordinate, it's going to be 2 root 2. So that's the midpoint. And if we work out the gradient of that original line connecting the two, it's going to be, it's going to come down here actually, it's going to be 4 root 2 over 6 minus 10, which is 4 root 2 over 16, which is root 2 over 4. And therefore the gradient of the perpendicular bisector is going to be -4 over root 2. So that's the gradient, and we know that it passes through the midpoint. So if we want to find the equation of the line, it's going to be in the form y equals -4 over root 2 x plus c. Substituting in our values, we have 2 root 2 equals -4 over root 2 minus 2 plus c. So that's 2 root 2 equals 8 over root 2 plus c. And that gives us a value of c as being -2 root 2. So the equation of our line is going to be, and -4 over root 2 is just 2 root 2. So I think we should rationalize it, probably make it slightly neater. And that gives us y equals -2 root 2 x. Actually, probably better to write that as 2x root 2 to avoid confusion about whether the x comes under the square root or not, and -2 root 2. So that's the equation of the perpendicular bisector, the red line here. And we want to now find the locus of points representing modulus of z plus 1 equals 3. So for that one, and I'll switch colour, so z plus 1 equals 3. We are looking at a circle with a centre at -1, 0, and radius 3. So we should know that that's going to be in the form of x plus 1 squared plus y squared equals 3 squared, which is 9. So those two equations here, those are the Cartesian equations that we're interested in, and those are our answers to part A. And part B is asking us to find the two values of z that satisfy both of the above. Is it? Yeah, both of the above. So to do that, we need to solve the two equations which I've just highlighted in yellow. We need to solve them simultaneously. So we can substitute in for that because we have one linear, one quadratic. So we have x plus 1 squared plus, and then here we have minus 2x root 2 minus 2 root 2 squared equals 9. So just expand out the brackets, x squared plus 2x plus 1, and then this bit here, just going to be really careful. So 2 root 2 squared is 8. So this is going to be 8x squared, and the minus signs will, minus times a minus will give a plus. And then we have 2x root 2 multiplied by 2 root 2. So 2 root 2 times 2 root 2 is just x, and then we're multiplying by 2. So this is going to give us plus 16x. And then we have plus 8 equals 9. So we have 9x squared plus 18x plus 9 equals 9. So 9x squared plus 18x equals 0. So 9x, x plus 2 equals 0. So x equals 0 and x equals minus 2 are the two that we're interested in. And we needed to find, is it two possible complex numbers? Yes, two possible complex numbers that satisfy both of these. So it's good that we ended up with a quadratic here, and that tells us that we're on the right track, as well as the fact that we just had nice values. So for x equals 0, y equals minus 2x root 2 minus 2 root 2, so it's just going to be minus 2 root 2. And for x equals minus 2, y equals, and then substituting in, we have 4 root 2 minus 2 root 2, which is just going to be 2 root 2. And therefore, the two complex numbers that z could be are z equals minus 2i root 2 and z equals minus 2 plus 2i root 2. And those are the two possible values of z. And pretty cool, I'd say, only to give you 2 marks for all of that. And finally, we need to shade in the region on an Argand diagram which satisfies both of these. So this is the first regions question that we've gone over in either of these two videos. And we have inequalities here. But it is similar to the question which we've just done, but instead we've got inequalities. So first things first, we're just going to draw an Argand diagram. Oh, and I think I need a bit more space as well. No, we can do it here. So we have our real and imaginary axes. And we are looking at, so for the first part of the inequality, the z plus 10 bit, it's similar to the perpendicular bisector, which we found in the first part, apart from one difference, which is the inequality sign. So if we just sketch on that perpendicular bisector, which we said was, had this equation here, minus 2x root 2 minus 2 root 2, is going to look like this. I'll sketch with a ruler better. So we draw a line along here, and that's the perpendicular bisector. But we've been told that it needs to be closer, essentially, to z plus 10. It needs to be closer to the minus 10 than the 6 plus 4i root 2 because of that inequality sign. So we're looking, if this was an inequality on its own, we're looking for this section here, which is this side of the perpendicular bisector. But there's also another inequality which we have to satisfy, which is that z plus 1, the modulus of z plus 1, sorry, is less than 3. So we said that we had our circle at centre minus 1, 0 and radius 3. So if I just get rid of the shading for a second, then we have a circle at minus 1, so somewhere around about there. There. And if you're drawing these in an exam, you should probably be more accurate with spacing and stuff like that, but it's kind of hard to do without labelling axes properly. So we have minus 1, 0 and radius 3. So it's going to be somewhere, that was terrible, it's going to be somewhere like that. Yes, that is a terrible circle. But we're interested in the part inside the circle because it's where the modulus is less than 3. So, and we've got solid lines here because of the inequality signs. And we're interested in this shaded region here, which is what we need to shade in. But do be more accurate if you're doing this in an actual exam question. So in this final question, this is the biggie, we have a set of points that lie within the shaded region, including its boundaries, is defined by, and then we have an inequality, which matches up with this shaded region here. But we've got unknowns in this inequality. We've got A, B, C, and D, which we need to find. And so I'm going to start by recognizing that the center of both of those circles is at center is minus 2, 1. And for the smaller circle, the radius is clearly 1. And for the larger circle, the radius is going to be 2. And that gives us all the information that we need to straight away fill in the values of A, B, C, and D. So A is going to be, actually I'm just going to write them down here. So A equals going to be the radius of the smaller circle, which is 1, because we've been told that the modulus of this number is bigger, and for it to lie in the shaded region, therefore, it must be greater than a distance of 1 from the centre. B is going to be 2, and C is going to be minus 1. Remember that we switch the signs around when we have those modulus signs, because that's the way we work to find the centre of the circle. And D is going to be the radius of the larger circle, which is 2. And so that's the answer to part A. And part B, the harder part, we have been told, and this looks really scary, but it's actually, this is exactly the same as what we've just seen. And this bit here is also quite easy to decipher because it's just the idea of a perpendicular bisector again. So we've been told that the set Q is defined by the region where this first one and the second one are both satisfied simultaneously, and we need to determine the exact area of the region defined by Q, giving our answer in the simplest form. So this bit here tells us that we're only looking at parts in the shaded region on the diagram that they gave to us. And this bit here is going to be the perpendicular bisector of 0, 1 and 0, 3. And the midpoint of those is 0, 2, and the gradient is, well, I mean, it's quite clear that it's going to be, even without this, we have the perpendicular bisector of this point and this point. So the line joining them up is going to be here, and therefore if we want the perpendicular bisector, it's going to be right across there going through 2. So literally just there. And just to quickly check the inequality signs again, we have an inequality sign saying that it's closer to 0 minus 1, to 0, 1 than it is to 0, 3, which means that we are looking for the area which is in the shaded region and below this line. So in other words, we are looking at this region here. So this whole section, and we need to find the area of that section. So how we're going to do that, and it does take quite a bit of thinking to reach the solution for this. So one way of doing it, so I mean, it's going to be quite straightforward to work out the area of the shaded region they gave to us to start with, right? It's going to be the area of the larger circle, subtract the area of the smaller circle. So that's quite easy to work with. And if only we had a way of working out the area of this section here, that bit there, that would make it, we can then subtract that from the area of the shaded region to get the area that we're interested in for the question. And this area here is a segment of the circle, and then we can find a sector that we can work out this segment from. So for example, if we tried this sector here, this wouldn't work. And the reason why this wouldn't work is because we don't actually know, if we try to apply our GCSE method of solving this, by working out the area of the sector and subtracting the area of this triangle, we don't actually know the lengths of any of these triangles because we don't know the coordinates of any of these 2 points. And therefore there's simply too many unknowns, so that isn't going to work, unfortunately. However, there is also another sector in this diagram, and it's right here, coming down here like this. This is a sector which we can work with, and we can work out the area of the triangle, work out the area of the sector, and then work out the area of the segment. So I'm just going to come down here and redraw it, so that we can work a bit more easily. So we have this sector here, and we know that, and I'm also going to split this down the middle, which might make it a little bit easier to work with as well. So we know that the this length here was the radius. So this is just going to be length 2, because it's the radius of the larger circle, and this is also going to be 2. If we want to look at the dotted line, I'm just going to go back to the diagram. That is going clearly from the center of the circle up 1 unit. So this length here is 1. And then what we're working towards here is to work out the area of the triangle part, which we're going to calculate using half AB sine C, where C is this angle here. And since we've got two right-angled triangles, we can work out this angle, double it, and that will give us the value of our angle C. So for this, I'm going to label this angle alpha, this small acute angle here. And in order to find alpha, we're going to use some basic trigonometry. So cos alpha is going to be 1 over 2, because the yellow highlighted one is the hypotenuse. So alpha is going to be inverse cos of a half, which is 60 degrees, exact trig values. And so the value of C is going to be 60 times 2, 120 degrees. And to find the area of the triangle then, based on that, the area is going to be half times 2 times 2 times sine of 120, which is going to be, well, it's going to be 2 times sine of 120, which is root 3. So that's the area of the triangle. And to work out the area, yes, I'm just going to label this area of triangle. And to work out the area of the whole sector now, this is probably the easier bit. We know that it's just a quarter of the area of the full circle of radius 2. So the full circle would be pi times 2 squared, but because we've only got a third of it, we need to multiply by a third. And that's going to give us 4 pi over 3. That's the area of the sector. And this is the area of the triangle. So if we want to find the area of the segment, we're going to subtract from the area of the sector the area of the triangle. So 4 pi over root 3 minus root 3. That is the area of the segment. And finally, just to go back to the question, it's important to remember that that was not what they were asking for. They were asking for the area of the area below, the region below the line, minus that unshaded circle. So, if that's the area of the segment, we now need to go back and work out the area of the initial shaded region. So the larger circle has area equals pi, and the radius was 2, so it's 2 squared, which is 4 pi. And for the small, and for the smaller circle, the area is going to be pi times 1 squared, which is just pi. So the shaded region, the initial shaded region, we're subtracting pi from 4 pi, so we're left with 3 pi. And to then, if we know the area of this part here, then we can subtract that from the whole shaded area to give us the area of the region defined by Q. So now we're doing 3 pi, I'm just going to switch colour again actually, 3 pi minus, and then what we defined above, 4 pi over 3, 4 pi over 3 minus root 3, which is 3 pi minus 4 pi over 3, add root 3, which is 5 pi over 3 plus root 3. And that is finally our final answer to the area of the region defined by Q. So it's quite a tough one, but it is doable by splitting it into shapes that we know how to calculate the area of. Calculating the area of the shaded region, so the initial shaded region, was never going to be a problem. And from there, it was just working out the area of the segment. There was a tricky bit, but this idea is a GCSE idea of calculating the area of a segment. It is a GCSE idea, and all we've done is combined it into Argand diagram's context to work out the area of the region defined by Q. But it isn't that difficult in nature. It's not that difficult. So we've now reached the end of the Argand diagrams questions. And in the next video, I'll be covering some series questions, which should be a bit easier than these. But honestly, the best way to improve at this loci business, regions, and Argand diagrams is to practice. And often to think back to those coordinate geometry as well. So in part one, I gave some of my tips, which helped me when I was studying this topic myself, so feel free to look back at those. And also, please leave any of your own advice in the comments for other students to benefit from on these questions or anything else in further maths. Anyway, that's it for this video. Hope it helped, and thanks for watching.